Morning, everyone. This is the second presentation of 7. We are approaching these in order from the basic beginning, the Big Bang, to ending up with some specific topics of using machine learning as the next step in seismic interpretation. Thinking about seismic interpretation in the broad sense, not just to pick a few horizons and use it as a kiss and a prayer. No, it's a little bit more sophisticated than that. Not sophisticated just to sound phony, but sophisticated to dig a little deeper into the data. And with spending all that money that we do on our geoscience data, put it to better use. So the second part is an introduction to sets and set notation. And I'm sure I'm going to lose all of you at some time in this presentation today. So don't worry if you feel like your eyes are glazing over. The next to the last slide and the last slide have something to do with geology. And we're setting the stage of every single step here of why it has some value with machine learning ultimately, and having the value for doing a better job of seismic interpretation. And the best way to describe machine learning is with sets and set notation. But I got a surprise for you, so let's get started. We're going to start off at the big end here with sets. Just what is an object and what are properties of objects? So we know that the universe is filled with objects, isn't it? I don't think that's any surprise to anybody. Every object has one or more descriptors. And so we're going to use this terminology quite a lot. Objects and descriptors of objects. Objects have no names. Don't come back and ask me, Tom, what was it that you said a while ago about what is an object again? An object could be anything. And that's literally true, anything at all. Mathematically, we know that the universe, because of the Big Bang, it had a beginning. So the universe contains a countable set of objects. Holy cow, that's a big number, but it is finite, so it's countable. And it's unordered, of course, meaning that what we have in terms of the universe is a universe of objects that can be discussed in any order that you want. So we're going to draw the distinction here. If we have a universal set of one kind or another, like objects, this bracket right here, the curly bracket means an unordered set. And the fact that it goes from 1 to n, in other words, it has a first and a last, well, that means that it's a countable set. So we have then the curly brackets indicate an unordered set, and we'll use square brackets to indicate an ordered set. Okay, now what about the next part here? What about a descriptor of an object? Well, an uncountable set of objects, descriptors. Descriptors are just labels. Nothing fancy there. Don't get glazed over yet. The descriptors of an object. Well, how many descriptors can we have of our objects? The objects are countable. The descriptors are uncountable. They just go on forever. You can have the, red oranges and red heavy oranges and red heavy but rotten oranges, that sort of thing. So the descriptors are infinite. Now, the objects, when we use this bold double strike here, this font, these represent the objects that can't be reduced any further. These are the big boys. The objects O and the descriptors set, D of O, they cannot be a subset. What is the universe? Holy cow. The universe is itself U, and it is a set of all the objects and all the descriptors. The objects is not empty, and the number of descriptors is an infinite count. The largest set of the objects is a set of 1. In other words, U, that's one object. That U stands for everything in the universe, everything. All the objects and all the descriptors of objects. It's the universal set. Yeah, there's nothing bigger than that. All right, so that's starting from the big, and we're working our way down from the large to the small. So sets, we're going to indicate those with the symbols, and members are lowercase. I'll give you an example of that. If you have a set of one member, for example, this is the set A, which has only one member in it. And it's a set, so it's a capital A. They're bold and they're uppercase, and a member is lowercase, and it's never bold. But in the case of where you have only one element in A right here, then it's okay to use a lowercase capital A as well, not bold, unbold. Now, countable. Countable objects, they're in the universal set, so this is a working subset, O, which is indicated with the ordinary font. And then we have similar and dissimilar objects. A set of dissimilar objects do not have a descriptor, but it's a set of objects in the universal set, but the descriptors equals 0. In other words, this is null. So this is just an example of an object only and no descriptor at all. We also have a situation where we've got a descriptor for an object, a particular object and a bunch of descriptors. So we have say a pair of descriptors, for example, A and B, for example, two descriptors for the same objects. Well, commonly we'll talk about how many objects are there, call that big N, and the number of descriptors. We'll commonly call that M. Say we got, in this case here, two descriptors. And for every object, it has a pair of descriptors. What does that mean? Well, every object, if you've got two descriptors, at one object with two descriptors, so that means is that descriptor set itself, well, A is your first descriptor, that's the member for sample N, and then B is the other one, and that's sample N. And this is the indication for that. And in this case, because we have A and B, that means is that we have an ordered set here. The descriptors are A first and then followed by B. If the properties are ordered, then the objects have to be ordered too. Well, okay, this is a little crazy. Let's, if Tom has gone loony, and you have perfectly good right to conclude that. So let's start off with, oh, by the way, does anybody recognize this picture? Where we are looking in out into the universe, anybody recognize this?
Is that our galaxy?
No. Oh,
We're zoomed into.
Hey, for us to look at our galaxy, if that's a Milky Way, we'd have to jump in a rocket and fly many light years away. So no, sorry, Deb.
We're zoomed in as far as we can to an empty black part of space, and then we found all these galaxies. I forgot what it's called.
This one is the Andromeda galaxy, and it's like our twin sister to the Milky Way. And someday we're headed towards Andromeda, and someday we're going to pass right through the middle of it, and it's going to pass through the middle of us. So right now it's like us, it's a barred galaxy. See the bar across there? And the Milky Way is also the same way. It's a barred galaxy. Bars usually come from the fact they may be spirals, but they have run into something, and there's some dust and some stars that have collected near the nucleus of their bars. And it happened to both Milky Way and Andromeda. And this little thing over here, I think, is the little Magellan. But anyway, let's get down to business here. Here's an object, and here's another object. Are they the same? No, they're not the same. One over here on the left, the fuzziness indicates that actually is not a single star, but that's a galaxy, just like Andromeda. Well, what about this red, quote, dot right there? It's red, and the red indicates a very large Doppler shift, indicating it's far away. Is it another galaxy, or is it a single star? So far away, we really don't know. Probably another galaxy, but so far away, it's way back there near the beginning of time of the Big Bang. So here's the point. This business about objects, and that is that we're pointing at this one, and we can point at that one. We point at two objects, but we can't really talk about them until we have some labels. So this we know, this object is a galaxy, and this one is something questionable. But at least we have some labels, and then we can talk about them. Then we can understand them. Now, what about this baby right down here? What is that? Well, it's an object. That is an object with a label. That's Andromeda galaxy. And it's a set of objects as well, of course, because that haziness is, if we were to zoom in even further, would be a very large group of stars. So what we have then is that we have a subset with the descriptor because there may be other galaxies. And that's why we have galaxies are a descriptor, and this is a subset of the collection of descriptors of galaxy as the object. Next thing to think about on this is sets can be naive and axiomatic. Nice big fancy word, but there are many uses for sets and thinking about sets in terms of describing things. What does naive mean? Well, it's like an informal way of describing a set. You're not using all the mathematical niceties, whereas axiomatic, you're really a mathematician with well, I was going to say squeezing your tush, but that would not be very polite, would it? But axiomatic means that it's very precise, very formal, very legal. Like it's a formal definition, including axioms, rules, and extensions. Hey, there's nothing wrong with thinking about sets and using sets. I would urge you to start thinking about using sets a little bit more in your thinking. It's amazing how it just works into your thinking about things. So naive set theory is, let's just knock out a good idea and we'll describe it using sets. And here we have a legal team that would be putting together an axiomatic description of a set, but doing it axiomatically. And why in the world would they do that? Well, you hire a fancy legal term for your will, don't you? And for a deed to some land, don't you? It's not naive. You don't scratch it out on a piece of paper. I hope you don't do that way, because you may, if you've got an axiomatic legal document, maybe scribbled on the back of an envelope, you think you may have some land somewhere, where in fact you really don't. So the point here is that there's the values of both of these. In a nutshell, the most popular type of a set is called ZFC, stands for Zermelo and Frankel, were early descriptions of a set of starting points. That's what axioms are, by the way. Zermelo and Frankel said, we have to start somewhere. And I think they came up with 8 or 9 different axioms. And they say, these are the most irreducible point. We have to have a starting point here, and we can't boil any more description of this. These are absolutely small, as small and as complete as possible. C stands for choice, and that is Zermelo-Frankel, that set of axioms, including C for choice. Well, that's being able to add the concept of making decisions. I choose this and I don't choose that. I'm telling you, this is real basic stuff. Well, so is the universe. Here's the universal set of 1. And there's all sorts of things that we could have here. B's, those are binary decisions, yeses and nos. And 0 are the natural numbers starting with 0. And 1 starts with the countable set starting with 1 through infinity. 1, 2, 3, 4, 5, 6, 7, 8. Z, those are the integers from minus infinity to plus infinity, yada, yada, yada. But then we get over to some other stuff here dealing with symbols. And then, of course, the empty set. We have logical connectors, yada, yada, yada. I'm not going to bother going through all this stuff. But, if you're thinking about being brave and describing something in terms of sets, we're not talking about partial differential equations or any of the other monkey business. We're talking about geologic stuff. And you might want to make a little mark here, because this is the ZFC axioms and the standard symbols, but with these little additional things here about brackets, ordered and unordered, and then the whole concept of cardinality. And then this is the symbol of the lower half and the upper half. That's range. Uncountable set looks like this. Countable set looks like that. All right, now let's move on to set builders, because that is the way people describe these things, and that's how you write a mathematical expression. We're not talking about algebra. And as I said, we're not dealing with the differential equations at all. On this, we're talking about geologic stuff, describing sets. And this is the standard form for what's called a set builder notation. It's like a set. If you've got a bunch of a geologic column, for example, that list is a set. And now you can describe it. You can just give it a name. And by the way, you don't have to use single letters. You could say the set name is Geologic Column of Southwest Texas or something or other like that. You can make it as complete as you want to. But the set itself is equal to an unordered set with a left and a right side. The left side defines the members of that set, which could be just a list, or it could be two-dimensional, maybe XY map coordinates, or who knows, maybe it could map location in this as well as a depth on a borehole, that kind of stuff. L is the members of the set, and then R, the right side, describes the members. And a complete set builder goes all the way up and includes the universal set U. So that you take whatever you're talking about here, and then it is a member of the universal set U. Okay, that's what set builder notation is. And it may be perfectly opaque at this moment, but that's okay. That's okay. Just don't fall out of your chair yet. Because I'm going to show you some what I think are cool examples. I hope you buy it. All right, the next important thing to have here is an indicator function. Wow, what the heck is an indicator function? Well, an indicator function is really simple. Indicator function is a mathematical statement of counting. If you have a set and you've got maybe a honeydew list for your squeeze, and the honeydew list has 5 items, okay? Well, the indicator function, if you just have that honeydew list, the indicator function delivers X, in that case, is your honeydew list, and the indicator function will count for it. And it will say, for this honeydew list, the third item right there, it equals a 1 or not. So for example, let's say that we've got a descriptor D, and it's a set of 1, 3, and 5. And then the indicator function, the third element of that set, of that 3, is the third one, the number 3 or not. Is the third one a 3? And you say, yep, yes, it is. So indicator function says, yep. But is the indicator D 4? And the answer to that one is no. It's not a member of this set at all. And that's how you use the indicator function. You're probably familiar with the stuff of using functions. Indicator function, it looks a little weird. And what makes it kind of weird is that it's delivering a number based upon being a function of something else. Now, if you think about like sine of degrees, we know that the value is 0.5. Well, 30 degrees and the sine function, that's like taking degrees and the function sine is converting those from degrees to a number, 0.5. Well, that's all about. Well, here's a apparently intimidating example of a set notation. And we ask ourselves, what in the world is it? Well, it's the set notation. The left is the description of this set, and the right has a left part and then the right part. Okay, all this stuff that goes along here, right there. Don't fall asleep on me yet, but it is a complete mathematical description. I'm going to probably surprise you a little bit here when we get done what this statement, mathematical statement says. But what it is a mathematical algorithm, and it has something to do with Kohonen SOMs. And he wrote a whole book on the subject of self-organizing math. This is a real key function, it turns out. This is a statement, mathematical statement of Kohonen's description of finding the winning neuron that's closest to a particular sample. In this case, the sample is X. That it's an IJK. It's located in a 3-dimensional cube right there. And the winning neuron is calculated, given this location in the 3D survey, what's the nearest winning neuron? This is a mathematical statement about that. Now, Kohonen didn't use this mathematical notation at all. And yet, if you're going to write up the code, if you're going to make anything out of this, you'd have to read Kohonen's book, figure out what he's talking about, take all that verbiage, boil it down, and then write yourself a code. Write it in Python, write it in Fortran, write it in Swahili, write it with whatever you want. So what we have here then is a mathematical description that is general purpose. I'm not going to just get too distracted here, but I know there's all sorts of pseudocodes and things like that, that if you've been writing algorithms for years, there's been all sorts of attempt. This is evolving as a standard description of mathematical algorithms. This is the way to put them together. And it is simple. It tells us that the nearest winning neuron, W, is W sub PQ, and it is finding the one with a subscript P and Q that is nearest X. In other words, the distance here, this double bar is a Euclidean distance. So the distance between X and any W there is as small as possible. It's the one with the P and the Q that minimizes this argument right there for all winning neurons in the set of winning neurons. That's what that's all about. You can start to read this stuff. All right. So we have then is the result is a winning neuron, and it's bold because it's an attribute list. It's a vector. And the parenthesis indicates a function of X. X is a set, certainly. And here we have it described in set builder notation. So here's the bottom line. I urge you to think about sets and set notation. Why? Because they're replacing the starting point of nearly all parts of mathematics. Can you imagine that when you went to school? That here's something that's come along. It first came along with George Cantor in 1905 or something or other like that. And here we are just a little bit more than 100 years later, and it is a complete upheaval of mathematics. That it is sets and set notation is more fundamental than algebra. And I think you've probably heard me wailing away about that before. Sets and set notation are replacing the starting point of nearly all parts of mathematics. Just to give you an indication that it's true, hey, you can Google just as well, maybe better than I can. And I just Googled some requests of what are sets used in junior high schools. And this is what I got back. I got back this, the De La Salle Lipa Integrated School. This is the mathematical program for math in the grade 7, an introduction to sets. Hello, where is this place? Well, just Google map it. You can copy paste this in. Here it is. It's south of Manila on the island of Luzon. Introduction to sets, grade 7. What are sets? A set is a collection of well-defined objects forming a group. Grade 7. Sets, elements, cardinality, well-defined objects. The set has elements and upper and lowercase letters, and cardinality is how many of them are. Hello, introduction to sets, grade 7. I don't think I need to whip on this anymore, but get the idea? Kids are being taught this early because it's so fundamental. This comes before algebra even. Now, what does it mean for us? Well, it kind of comes in 3 parts for us. There's data samples, and then we got data sets, and then spaces. Hello. Let me explain a little bit what I mean. We got some input data. Maybe we got a log curve, and that's our sample at a particular depth, index I right there. And then maybe we're going to process it a little bit. Maybe we're going to do some classifications. So we've got an input and we've got an output. Input X sub I, output at that same depth is going to be Y sub I. And we have a descriptor that we're going to be working on, and we might have some purpose of maybe finding the probability of something. So the second level then is if a single sample is a small X sub I, the whole set itself, in this case, it's an unordered set and a large bold set, and that is then on the data set level. And the third part is the data set is part of a universe. You know, hey, we think about this all the time. We got a reservoir. We got, 158 wells. Okay, hello. There's nothing fancy about this. That reservoir that we're dealing with, say 148 wells. maybe the state of Texas, we got 246 reservoirs to be dealing with, that sort of thing. How many do we have in the United States? Once you start thinking about sets and subsets and get this firmly in your mind about everything from a single number all the way to all different levels of grouping, it puts a little swagger in your thinking. Let me just leave it at that. All right, but let's not lose track of where we're headed. So where are we headed? Well, are we trying to show some geophysical results? If you want to be a geologist and not interested in geophysics, that's fine. There's nothing wrong with that. You've heard me point out any number of times that I think with the tools that are being developed for machine learning, it's much more valuable today for seismic interpretation to understand your geology, recognize geological features even more than geophysical results.